Can everybody hear me? Okay. So, having fun with coroutines. Before we get started, who here has heard about C++20 coroutines? Show of hand. Okay, keep your hands up. Who has used some coroutines in C++? Okay, considerably less people. There's still a few hands though. So who has implemented a custom coroutine type? One show of hand. Okay, so this will be pretty new for pretty much everybody. So, but most of you have heard about coroutines at least. So let's start with a few statements, and let's start with the first one. Coroutines enable something that hasn't been possible before. Who thinks this statement is correct? 2, 3, 4, 5. And I see some heads. So yeah, okay. Who agrees with the second statement? Coroutines are about async code. 1. I would have expected more hands here for a simple reason. Pretty much all the talks about coroutines you will find are only about async code. But to go a bit into this, coroutines don't enable anything that wouldn't have been possible before. Though writing that stuff without a coroutines feature in the language would be a considerable amount of code you have to write. Like whole bunches of boilerplate you'd have to repeat every time. But there's nothing coroutines enable that wouldn't have been possible before. To the second statement, coroutines are not about async code. Coroutines are not even async in itself. They are a synchronous concept. They map pretty well to some cooperative features and concurrency, but they on themselves are not about async code. So let's get started. We always pretend that C++ coroutines are something pretty new, and that by definition means coroutines in itself are something pretty new, which is kind of correct for all the languages you encounter. All of them gained coroutines pretty much recently, within the last 10 to 15 years. But if we look at the history itself, coroutines are decades old. Like, they were invented back in '58. By Melvin Conway to parallelize a COBOL compiler. Anybody here knows what COBOL is? Okay, pretty much everybody. So he invented this thing to speed up the compilation of a COBOL compiler because those are multi-pass like the C++ compiler. But then a pass was, okay, we have the tape, we run a pass and it's back on the tape. And then you take the tape and start the next phase. Fun. And with his implementation, it was possible to load the tape and get the end result in one pass. So he invented that. 5 years later, he wrote a paper about it. And surprisingly, the paper actually influenced people. Like, we always point to similar as the language we stole our idea of object orientation from. In reality, Similar didn't start with object orientation, it started with coroutines and only gained object orientation a few years later down the road. And then lost coroutines, pretty much. So that brings us to 65. And for us in the C++ world, nothing happens then until in 1972, there's the C thingy. Obviously no support for coroutines. And after that, there's this thing called C with classes. And C with classes is interesting. If you read D&D, there's this funny statement of the first library ever implemented in C++ was a task system enabling a coroutine style. This was an object-oriented library, but even back then, Bjarne was onto coroutines. Which is funny because in '98 we got the first standard and there was no task system, there was nothing about coroutines. And it stayed that way for decades. And the first mentioning of coroutines for anybody outside of the committee was in 2017 when there was the coroutine TS, which for me came out of nowhere. What? Coroutines? Why would we need that? What would we do with them? Well, people thought we need them, and only 3 years later we got coroutines in C++20. And ever since, there hasn't been too much adoption, actually. I mean, in 20 we only shipped low-level stuff, and even the standard today doesn't provide you much high-level stuff about coroutines. But at least we got the low-level stuff in 20. So what actually is a coroutine? And to talk about what the coroutine is, we actually need to talk about functions first. What is a function? Well, on an abstract level, a function has two operations. Operation one is we can call another function. And what that does is it suspends our function and activates another function. And that function takes control of the computer until the second operation happens, which is return. At that point, we cancel the function we're currently in and yield back a value. And by yield, I mean throw an exception, return nothing, or return a value. That's a function. What is a coroutine? Well, a coroutine has three fundamental operations. It has call and return. So we can call a coroutine. But it has one additional operation, which is we can suspend. What suspend does is we suspend the current function we're in. We return a value to the user. And later on, the caller can call us again. But calling us again is just another way of saying call, so that's not really a fundamental operation. That's the basic model how coroutines work in C++ and pretty much in general everywhere. Yeah, can return. So how do we do that? And there's pretty much two ways to implement that. And they are called stackless and stackfull. And where the names come from will make sense in a minute. So a stackless coroutine is pretty much something that looks like a function, but its state is actually not on the call stack, but on something we call the coroutine frame, which is some dynamic memory allocation somewhere. And everything, its local variables, its temporaries, its inputs will be in there. But this thing will execute like a normal function from the point of view of the computer. A different way to do this is stackfull, which looks something what like a user-level thread that you can schedule on a kernel thread. And obviously, here the normal rules of languages apply. So inputs are on your call stack, all your temporaries are on your call stack, just like it would work for a normal function. So this one distinction has interesting consequences. For a stackless coroutine, we can only suspend directly in the function. If you have a stackless coroutine and you call another function, that function can say, okay, we suspend now at this point. Suspension can only happen directly in the coroutine. For a stackfull coroutine, we could actually do that. We could be arbitrarily nested on the call stack and do, we'll suspend now and another thread must take over. Stackless coroutines need language support because the code you write and the code that actually happens on the machine are vastly different. Like there's extensive compiler code generation going on at that point. Whereas a stackfull coroutine can be implemented as a library. Boost alone contains at least two, which are coroutine and coroutine 2, and I think there's 3 more around ACU and some other Boost libraries. All of them depend on some context switching library, but in general you can do this as a library pretty easily. Easily as in you have to write some assembler. That's because, so in C++ coroutines are stackless, and we have 3 new keywords that have this nice co prefix. And if you want to know where we need that, that will be something I can answer after the talk. That doesn't mean stackfull full coroutines aren't actually interesting because depending on your domain, stack full coroutines may be what you actually want. Which is why there's a paper going through library evolution for years at this point and is finally targeting C++29 that will enable us to do a framework that you can then use to implement your own stack full coroutines types. And per the naming convention of the standard library, we decided to call these things fibers. Those of you who have used the When API at one point in your history will know that they had this all the time. There's a fiber library within Windows that does pretty much what I'm describing here. So, how do we write a coroutine in C++? I hope the code is big enough. Okay. So, in C++, the simplest coroutine we can write is we have a function that returns something I've called here coroutine, and we do a co-return. It's the simplest way we can do a coroutine. And there's some things you should notice here. First of all, there's no marker on this function. Like, it's not saying coro, it's a function, which would tell you it's a coroutine. So being a coroutine is a pure implementation detail in C++, which allows you to write something like this. And if I show you this declaration and ask you, is this a coroutine? The only answer you can give me is, I have no idea. In this case, it isn't. It's calling a coroutine, but isn't itself a coroutine. There's some other stuff going on here. Notice how the co-return doesn't actually match what we're returning. Like, my func says it returns a coroutine object, but my body only does a co-return. What object is actually returned here? And this return type is of utmost importance. It cannot be deduced, it must always be specified, and it will control what's actually valid inside the code body of the function. And that's pretty much everything you can do in C++20 with coroutines, because there's no high-level library for using coroutines in C++20. Thankfully, we no longer use C++20. Well, I know some of you are not even using C++20, but everything I'm going to show you now that the standard library provides, you could pretty much do on your own. And in 23, we managed to ship one coroutine type, which is a generator. Generator is a coroutine type that represents an input range, so you can only traverse it once. The body is executed to the next co-yield statement every time we move the iterator. And we can use it like we would use any view or range. Notice co-return can't produce a return value. We can only use co-yield to return a value from a generator. And notice this co-return is actually optional there because if you can only write this co-return with a semicolon, it's optional in a coroutine. Co-await isn't supported in a generator because they're synchronous. And co-yield produces the next element we are going to use. And there's one funky thing, which is we can use this thing called ranges elements of to yield a complete range. And that allows some optimizations depending on what kind of range you're actually iterating over, and will make this more efficient than doing a loop here and doing an element-wise yield. And that's an exhaustive list of everything you can do in 23 with coroutines, unless you roll your own. In 26, by some heroic efforts of some committee members, we're going to get another type, which is execution task. The namespace execution means this is something to do with sender-receiver stuff. So we're not going to talk about sender-receiver today because sender-receivers alone takes 2 hours to explain for anybody to actually get it. So this models an asynchronous type-erased sender. And that thing will be executed on a scheduler. And if you don't know what those 2 words mean, I can't help you right now. Because I can't explain this within the time frame of this talk. Notice that once we have a task, we have no way to easily execute it because the task has essentially no operations. We can pass it to the sync wait thing, which is just a way from sender-receiver to wait for something, but task itself has no operations. For task, we use coroutine to yield the result. We use cowait to wait for a sender and a waitable, whatever those mean. And normally in a task, using yield makes no sense. A task will pretty much run until the coroutine happens, or it must suspend because there's some other thing it needs to await on. So you would be expected to think that, okay, co-yield is not supported. There's something going on here, which is co-yield is actually used for a customization that is hard to explain without understanding sender-receiver, which is it's pretty much abused to signal we are canceling this task without throwing an exception. Because normally if you want to cancel a coroutine, you need to throw an exception. And this is highly sender-receiver stuff. I'm not going to talk about those in detail. But that shows how much customization is actually going on there on top of the coroutines. And that's everything that you can do in C++26 with coroutines. So we have 2 types and a whole lot of open source libraries that implement something. For example, there's something in ASIO, there's some other libraries, but all of those have one thing in common. There are certain things you need to be absolutely aware when using coroutines. And I've grouped these together, and let's talk about keywords for a second. Say I have a function or coroutine, and I'm doing a branch. And in one branch, I'm doing a coreturn, which means this should be a coroutine. In the other, I'm returning the result of another function. Is this fine? No. This is not allowed because the compiler would have to dynamically figure out whether this function is actually a coroutine or not. So return is banned in coroutines. Okay. Thankfully, I can do compile time branches in C++. So, if const expr, is this fine? It should be fine, right? There are people on the committee who think this should be fine. But it isn't fine, because there's a simple rule in C++ that tells you you are not allowed to use return in a coroutine, even if that statement would be discarded. So what the compiler is doing, it figures out there's a compile time branch, and instead of just going, okay, I'm not caring what's going on down there, he's still parsing it and figuring out he's using a return, that's not going to work. Workaround here is you need to split this into 2 internal functions. And there's currently no other workaround here to use a structure like this. Okay, so simple rule, we can't use return in a coroutine. Another keyword that's interesting is noExcept. We have a function that's obviously a coroutine because of the coreturn. Is this fine? Syntactically, this is fine. We can mark coroutine noExcept. But remember I said there's this coroutine frame thingy where we store our stuff. And for obvious reasons, our stuff can't be on the stack because a coroutine will be suspended. Well, there's a dynamic memory allocation. Who here remembers what happens when that fails? Yeah?
Well, exception.
Yeah, there's an exception being thrown, which means we will terminate them out of memory, which doesn't sound too great. But there's something else going on here which is interesting. Wait, what's going on out there? Okay, something else going on here. What if I throw in my coroutine code? Anyone want to venture a guess what's going to happen on that throw? Terminate. That's what we would expect from C++, right? We have a function, we throw, and it's marked no except. Obviously, we need to terminate. No. The coroutine body. So the coroutine itself can still throw, even though we marked it no except. Once we look into how coroutines work under the hood, it will make sense. Trust me on that one. So the question would be, how do I mark that this coroutine can throw? And the answer is you can't. There's no way for you to write this coroutine may not throw, unless you're implementing the coroutine type. Anyone want to look out if he's okay? Okay, so no except, not a good idea. By the way, similar things apply to contracts, but I'm not going to go too fine to contracts today. Okay, last example with keywords. Thread local. For thread local variable, I take the address of the variable, I yield. Does this assertion hold? If we remove this line, it's pretty easy, right? It would hold. We've taken the address of a thread local variable, and later on we are checking this, it would hold. This may hold, depending on what you are doing with that object. Coroutines are not bound to a thread. You could transfer this object to another thread and keep running it. And then those two variables would not be the same object. So using thread local or anything else that's thread specific, like a mutex in coroutines, is highly discouraged. So, for example, holding a mutex across the suspension point, very bad idea. Okay, that is everything there is to know about keywords. What about arguments and parameters? So when I learned C++, I learned if I want to read a variable and not modify it, and I don't need a copy, what I'm going to do is I take it by const reference. Who else here has learned this rule? Well, pretty much everyone. So we may want to rethink that for coroutines, because this X may not live for the whole time your coroutine is alive. And that's not something we can statically check at all in the language. I've shipped code that does that, and the code has been verified that we never do a dangling in there. But I wouldn't recommend to start out with that pattern. So there's an easy rule here. In general, unless you know certainly that you're not going to get dangling, pass by value. In that case, X will be moved to your coroutine frame and will live as long as the coroutine object lives, unless the implementer of coroutine really messed up. Yeah, pass by value does obviously not work for types with reference semantics. Because types with reference semantic like string view, span, and we are constantly adding more of those things. Obviously, under the hood do this thing, and we'll start to dangle again. Okay. What about variadics? Is anyone here still using C-style variadics? Nobody? Good. They are not supported for coroutines. Like, this is the first time there's really something that doesn't support this at all. What about C++ style variadics? Well, those are fine. Insert, well, reference types, that's another thing. But in general, those will all be moved into your coroutine frame and live as long as your coroutine does. Which brings us to lambdas, which is one of the most fun topics when it comes to coroutines, because now there's two concurrent compiler transformations going on. Everybody here aware of how lambdas work internally? So, short explanation, they're transformed into a struct that has an overloaded function call operator. This capturing thing will transform all the variables you use inside the lambda into members, and the type that's going to be used for that members is defined by this reference, or if there's an equal sign there, by a copy. So, armed with that knowledge, is this okay? That's not okay. X is guaranteed to dangle here. Notice that we are capturing by reference, and our function returns a coroutine object, and we are immediately returning that object out of our function. So at that point, we are dangling. What do we do when a lambda dangles? Well, we capture by value, of course. That fixes everything. What does it? That's still dangling for a simple reason. If you have a member function, the pointer to the object you're calling on is passed by pointer. The object you're only referencing that object. And by that, the hidden this object will not be moved to your coroutine frame, and this will still dangle. The recommended way to combine coroutines and lambdas is by doing something like this. You do no capture and you pass everything you need in the lambda by the call operator. That works. That's totally fine. Insert statement about reference types. There's one other cutesy way how we can do this, which is this contortion. We capture by value, and since 23, we can say, you know what, I wanted this parameter to actually be passed as something other than a pointer. So here we are saying this implicit object pointer will be passed by value, which means it will be moved to the coroutine frame. And by extension, all the captured variables will be moved into the coroutine frame. Well, this works. This is combining like 3 different language features that are highly advanced. So you may want to go with the one on the top instead. Okay, something different. Let's talk about resource management. And I'll give you a second to think about whether this is okay or not. I see one thumb down. What do other people think? Second thumb down. The thumb downs are correct. If we were not talking about coroutines, this code would be safe. Because there's no way there's an exception going to happen here. So we would reach this close. But with coroutines, we don't know whether we are ever resumed. So if we open a file handle and then suspend and nobody calls us again, this fclose will never be reached. So that's annoying. Thankfully, it's easy to fix, though. If we, instead of the C API, use the C++ file API, this is totally safe. The stream object will either be destroyed when we reach the closing curly, which means we've iterated over the whole file, or if the coroutine was suspended and we destroy this object. In both cases, the stream will be freed. And that's pretty much all the caveats you need to be aware of when using coroutines. Which brings us to the second fun part of the talk, implementing our own coroutine type. Okay. There's been a whole lot of talks about coroutines on the internet. And the one defining feature of them is they either present some Hello World style examples, or they re-implement generator or something like task, which has painted this picture of, okay, there's no other use case for coroutines. Well, I think I found something really interesting we can do with coroutines, and that brings us to my day job. And I'm implementing something that's called a modeling kernel. You can think about it as something like a CAD kernel, but it's way more specialized. And the details don't really matter for what's going to happen now. In there, we have a function called sweep. That function takes a triangle mesh and a path and some other stuff we don't care about here, and returns us a vector with a new triangle mesh. It essentially does what's shown in this picture. So we get the mesh on the left and the arrows as our path, and we return the object on the right. This is a very compute-heavy operation. I'm going so far as to say the runtime is actually unbounded because it heavily depends not only on the size of the input, but also on the complexity of the input, which is something you can never actually describe in your API. So this can easily take minutes, and it can take hours. So you have something that can take hours. You better think about how can I cancel that? Because I don't want my computer to keep running for hours if I figured out, well, there's a failure in the input. Or we don't need this anymore. So how can I do that? Well, traditionally, we did it with a callback, either in the form of a function ref or some custom function pointer type, or we could use stop token, or it doesn't really matter what type we use. What will happen is we will do manual checking. So every few instructions in our code, we need to do a check. Are we actually supposed to keep going on? And if not, how do we actually abort the operation? Well, the easiest way is to throw an exception. That's abusing exception handling for something we shouldn't do, but that's way less of an hassle than doing manual unwinding and checking every return type and using something like stood expected. So neither option is really good. Is there a different way? And it turns out what started this whole talk essentially was one idea, which was, what if I could wrap this operation in a custom coroutine task type? And if I had a synchronous task, notice this is not the task that the standard library has, it's something completely different. I could do manual checking for suspension, and I could do automatic checking for suspension. And furthermore, cancellation is pretty easy. When we figure out we need to cancel the operation we just suspend, then the user still has this task object lying around, and we just destroy this task object, and the whole operation has been canceled without any stack unwinding or anything else going on. That was the idea. And if you want to design such a type, what you actually need to do is you need to think about the API, right? What makes this super complicated is coroutines have two APIs. The API you provide for the implementer of your function that does all these code statements, and the API that will be used externally. We are going to use something very simple. We'll have this task object, and we want to be able to wait with a timeout, and obviously this is going to be cooperative. And every time I run out of time, I want the coroutine to suspend and be able to do something else. And at some point, I want to be able to get the result of the operation. And what I want to do internally is, I want to be able to wait for another task. So I want to be able to say, this is my global task, and then I have subtasks in there. And I want to be able to have something like an async generator, and this is not std generator, that I can iterate over, and this should also be lazy and suspendable at custom points. Plus, I want to be able to do manual suspension checking, because sometimes we will have big batches of code where automatic checking is hard to implement. Yeah, and in the end, I want to be able to return what a task returns to me to the user. So this is the two APIs we need to support. And the question is, how would we actually implement this task type? And to figure out how to do that, we actually need to learn how the coroutine framework works internally. And this is a simplified presentation that gives you a good idea of what's going on, but ignores some minor details that would allow you to tailor your types even more. So, if we write a function that contains a co-keyword, it will be transformed into a new function, and the compiler will take our declaration and fill in a completely different definition. And that definition will look something like this. First of all, let's take all the argument types, and then we figure out what is the promise. Promise type is mostly a nested type. It could be somewhere else, that doesn't matter. A promise is what will actually allow us to customize what's going to happen inside this transformation stuff. So at certain points in the compiler-generated code, it will call on the promise to figure out what's going to happen next. And once we have those two types, we are going to define the coroutine frame, which is some internal type we are never going to see as a user. And then we will allocate that on the heap. And then we will move all the arguments that have been presented to us into the frame. And we're doing a force move here because some people think it's a good idea to pass by const value, and you don't want another copy for that. So if you pass by const string, you will still get a move constructor call and not the copy constructor call there. And then we finally construct the promise. And if you have a constructor that takes the arguments, you will get a reference to the now moved arguments. Otherwise, we'll call the default constructor. One of these two constructor calls must be valid. And once we've done that, we have our coroutine frame. And everything's set up to actually run our coroutine, which will happen next. And at some point, our coroutine will suspend. And then we will call the first operation of our promise, which has this nice name of getReturnObject. And getReturnObject needs to produce the value we can return here, which will allow the external user to keep hold of the coroutine and its frame. That's transformation number one. Notice how our body is gone. Because we use this declaration for a completely different function. Where's our body? Well, our body is in a new function somewhere. And it will be placed in there surrounded by a try catch block. And furthermore, our body is flanked by two try suspends. And we try suspend as there's potentially going to be a suspension point at this place. Whether or not the suspension actually happens there is decided by the promise by calling one of two functions. Notice our initial suspend happens right after we've set up our coroutine frame and before the body started running. And final suspend happens after the complete body has been executed. Okay, we have a try catch block. What's happening in catch is promise can customize what's going to happen here. Because sometimes you may want to throw and sometimes you may want to do something different. And if we do not suspend once our body has been executed, we are going to kill the coroutine frame. So the coroutine will delete itself from the world. Obviously, after this, we shouldn't keep using our coroutine. Something that's mostly implementation-wise is we will call this body every time we resume this function on our coroutine. And I'm using a GCC extension here to say this is the address of a label, and I'm now going to jump to the label. You can't take the address of a label in C++, but you can in GCC, and probably in Clang. So, transformation number 2. That leaves us only with one issue. There's still all these co-keywords in there. We need to get rid of those. The computer doesn't know what the code does. It knows how a return works. It knows how an if works. It doesn't know how a co-await works. What the compiler will do is it will transform all these three keywords, and those transformations are relatively straightforward. A co-return will be transformed into something like this. If we do a co-return semicolon or a co-return with something that is of type void, we are going to call the promise with return void. Otherwise, we are calling return value and pass in the expression you gave us. After that, we jump to final suspend, which is right before the final suspend call in the coroutine. For reasons that are not perfectly clear, your promise may not have both of these functions. So you need to provide either or, and the compiler will throw you in compilation error if you provide both. And it will also do that if they are behind a constraint. So you really need to make sure that those are not visible for the compiler in one type. So what happens to co-await? Well, co-await is a potential suspension point. And we will either use the expression directly, or if our promise has a member function called await transform, we will call that. Either case, we may need to produce something that will control whether or not our coroutine will suspend. And funnily enough, the easiest of all these transformations is co-yield. That's just, we call promise yield value. And it's a suspension point. So we've now seen everything our promise actually can do, which allows us to actually implement the first version of the task. This version will not support manual suspension, and it will not support nesting. So no recursion right now. And let's start really easy. We will have this nested promise type. And for lack of slide space, we will inherit from optional to have somewhere where we can store a result. And our task will have one member, which is a coroutine handle. Coroutine handle is pretty much a raw pointer to your coroutine frame. And the most important thing about it is to know that it does not support RAII. So if you think you can just write no destructor for this type, you will have a leak. Coroutine types are normally only movable because there's no way to copy a coroutine frame, because there's no definition of what that would actually mean. So we'll pretty much always have something like this boilerplate. Notice we can check the handle for whether or not it actually points to a living coroutine. So the first function I would recommend everyone to implement when they are doing a coroutine type is a function called valueless. That tells you whether or not you're actually managing a coroutine. There's some examples of some pattern like this in the standard library by now. There's this valueless by exception on variant. And for indirect and polymorphic, we went for a valueless function as well, because once your coroutine task is valueless, it will never have a value again unless you move it from another place. Then we will need our get. Our get obviously depends on this not being valueless. And it will call wait. And at some point we will call promise on a handle, which gives us a reference to this type, and the value is actually from optional. And well, wait is doing a synchronous wait. It's just resuming, which means we are now running the coroutine. So that leaves us with the promise type. Our promise type needs at least to have getReturnObject, which must return something that allows us to construct a task. And that's pretty much the boilerplate you will see all the time, which is, well, we have a promise object. We can ask the coroutine handle via a static function to give us a coroutine handle to ourselves. And then we need to implement unhandled exceptions and return value. Those are not that surprising. If an exception has been thrown, we just rethrow it, which matches the behavior of a normal function. And if we return value, that means we need to store the value somewhere, and then our coroutine will be completed. And for initial suspend and final suspend, we return these magic types called suspend always. Those will instruct the library that the potential suspension point is an actual suspension point. So we will suspend once before we come to our coroutine body and once we are done with our coroutine body. And that's pretty much it. That's if you can write that, you have understood 90% of coroutines. For doing manual suspension and recursive tasks, you need to actually understand what happens in this try suspend with. And that is, we will need something that's called an awaiter. And we will store that awaiter in our coroutine frame because we can't put it on the stack because the stack will potentially go away right now because we are suspending. So the first thing our awaiter must support is an operation called awaitReady. That tells us whether the thing we are waiting on is already done. Because if it's already done, there's no need for us to suspend. We can just grab the value that it's been awaited on. If we need to suspend, we need to figure out where our coroutine will continue on. Well, that's this unique label right after this if. Again, this is a GCC extension. You can't express this mechanism in pure C++. And afterwards, we need to figure out what happens now. And instead of just suspending, the awaiter actually can tell us what's going to happen now. And await suspend is a pretty special function because it supports multiple return types. The easiest one to understand is it returns void. In that case, okay, shut down. Just suspend this coroutine and nothing else happens. Alternatively, await suspend can return a bool, which is called conditional suspension. If this returns true, we just suspend. If it returns false, it means we just figured out in await suspend we don't actually need to suspend. And instead of suspending, we just jump down here. Going on as if we never thought about suspending at all. And the magic thing is, this returns something called some instantiation of a coroutine handle. And what's happening there is, the coroutine says, okay, we are shutting down. Instead of just stopping, run this thing now for me. So the coroutine can say, instead of me running, run this thing. That's called semantic transfer. That's like the hidden superpower of coroutines. So no matter what happens here, at some point later we will be resumed. This means we will jump here. And what happens here is, we will make sure that the awaiter is destroyed afterwards because we don't need it anymore. And its awaiter is only valid for this one suspension point. Differs as C23 proposal, 26 proposal. It's simpler than specifying this with a custom distraction guard, because that's like so much code. And before actually destroying the awaiter, we call the third function that an awaiter must have, which is await resume. And await resume will return the value of the thing we awaited on, which could be void, but could be any other thing. And it must be pretty much in this expression, because what it returns will be an expression. So once we know that, we can actually do suspension. We are now armed with enough knowledge to do a manual suspension. And let's figure out what we need to add. We need to figure out, is there something unclear? We need to figure out whether or not we want to suspend. And we are going to need a callback for that, because if you think about it, when we are calling wait on our task, we want it to run to the end, no matter how many suspension points there would be. So we are needing this callback, and then we will need a custom awaiter. And that awaiter is pretty easy. Await ready returns false because we want the wait suspend to happen. In await suspend, we just return whatever suspend returned, which tells us whether we can keep going on or not. And here's something special we see. The awaiter gets a handle to ourself as an argument. So the promise returns the awaiter, and when a wait suspend happens, the awaiter is called with a pointer to a promise again, which allows us to access this thing. And yeah, on await resume we do nothing. So that's pretty much it. That's how we can do custom manual suspension. And that's also pretty much it to doing recursion, apart from one thing. When nesting coroutines, there's something going on. And this slide alone has animations and took me a week. So we call this first coroutine that's going later to await on another coroutine. When we first hit the coroutine, we hit the initial suspend and will suspend, which means we come back here. When we will resume the coroutine, we will call foo, we will call initial suspend, we will call co-await, and we are back down here. Notice how both coroutines are in a suspended state. And bar depends on foo being called first, right? makes no sense to continue bar until foo has returned it a value. So when we resume, obviously we want foo to happen, which is not the case. Which brings us to the first thing we need to know when we're nesting coroutines. Coroutines don't stack automatically. Even though bar depends on foo being run, that doesn't mean resuming bar will resume foo. That's not something that's going to happen. If we want to have stack-like behavior, you actually need to implement it ourselves, which is not that complicated because there's only two ways where we can do a stack-like push, which are a weight transform and yield value, depending on whether we want to do stack-up push by core weight or core yield. Final suspend means our body has run, which means there's no way of going on with this coroutine. So at that point, we need to pop ourselves back up from the stack. And for resuming, we need to make sure to always resume the top of our stack. This doesn't happen automatically. And there's one more thing. Coroutines are not nested on the stack once they are suspended. So what does that mean? Look here while the next animation runs. So we are back at the situation. Both coroutines are suspended at where we left them off. What happens now? Yes. Notice how first only foo was on the stack, even though foo is technically nested inside bar. And later on, foo disappeared and bar appeared. That was symmetric transfer in action. That's something you will see all the time. And the fact that the nested coroutine stack is not on your actual call stack makes debugging coroutines a whole lot of fun. Like, you don't see what's actually happening inside the computer without a good debugger. So, now we know everything we need to do to actually do recursive coroutines. So the first thing we need to do is we need to have some internal stack management. The least we have to do is we need to have a pointer to the parent of our task, which is the task that waits on us. And if we are at the bottom of the stack, we need a pointer to the top of the stack, because that's the one we need to resume. And we probably need a function to skip along the parents until there's no parent left and we're at the bottom of the stack. And notice how we need to change weight to resume the top and not some coroutine. Then we need to implement final suspend and await transform to do actual stack management. So we need to custom await this. We'll look at them shortly. Then there's one last thing. We need to do exception handling. As the nested tasks are not on the stack, throwing an exception from a coroutine would actually now skip the task that's awaiting on our task. So we need to store a pointer to an exception and transfer it to our parent in case we have a parent. Okay. Two custom awaiters. So push awaiter manages the task we are waiting on, and we don't need to suspend if this thing is already done. Then we can just grab its value. Otherwise, we need to push other on the stack. It needs to be on top of the stack, which means we need to go to the root of the stack and set top to point to other. And then we need to point ourselves parent to other so we know who will resume us. So after doing that, we could just return other and keep going. But at that point, there may have been an arbitrary number of code being executed. So it may now be a good idea to do a check for suspension, which means we're already at root, so just call suspend. If we don't need to suspend, we just return other, and other will start running. But what to return in case we want to suspend? Well, we need a coroutine handle, and thankfully the standard library provides this nice function called no-op coroutine, which returns a coroutine handle that does nothing and suspends immediately. So after this has happened, we either got suspended or we will keep running on. In either case, at some point, this task will have to complete. And if it does, we add the pop operator. The pop operator is never ready because we need await suspend to happen, because we need now to remove ourselves from the stack. In this case, self is actually other. So, if we have a parent, we pop ourselves from the stack, and then we can check for suspension again. If not, we are just going to keep running this coroutine again, which means we come to await resume. Here we check, has other terminated via an exception? If so, we are now in the correct frame to rethrow that exception. Otherwise, we can grab its value and pass that to our user. That leaves us with that await resume down there. That's never going to be called. Other has final suspended with our pop operator, and right after this return, this object will be destroyed, as will our task. So await resume there is never called. And if we want to make that absolutely sure, we can put an unreachable in there. And that's it. So I've implemented that. I've also implemented the generator. Both of those are obviously generic. Both of those are recursive. Both of them are heavily optimized. Like task needs 8 additional bytes to store all this stack management thingy. They support allocators because there are people who care about allocators. And from experience, generators are way harder than tasks. Like really hard. So there's some potential extensions I figured out doing this. First of all, standard library types don't have this valueless for coroutine types. I've written a paper for task. I wanted to write a paper for generator until I figured out how completely bogus it is to add this to this type. There's existing implementations, and figuring out how you can do it in every implementation is not fun. But maybe there should be a policy-wise, so we can, for all move types, check whether they are valueless or not. Because we are getting an ever-increasing amount of types that do that. And yeah, I figured out fork await is actually not supported in the standard right now. That was in the coroutine TS and got dropped on the way for interesting reasons. And now I'm open for questions.
So, if you have questions, please wait for the microphone.
How many lines of code do you have in your custom coroutine library? And how many lines of code your tests are?
Well, the tests aren't that extensive right now, but they cover every potential use case you can have. This whole library is roughly 500 to 700 lines of code, because it turns out you can share like the majority of stack management, awaiters, and so on between these types. So you only need those ones. And it's actually figuring out how to implement those types once that's the problem there, especially for generator. So it's not a lot of code. The tests could use more work, but they cover every potential combination of how you can suspend and resume right now. The tests are not production ready. The implementation is not yet used in production, but there's little to no things that stand as a blocker before doing that.
Okay, more questions. Wait a second. Coming back to you.
So after your talk, I'm a bit surprised that it has not had a wider adoption, or not, because could you showcase a little bit how this actually improves the application code, and how much easier the code becomes by using your custom coroutines? Because this was I was missing this a little bit right now.
So it's hard showing this in isolation. So for something like an async task, it's pretty easy. Imagine every callback call you've ever seen being replaced by, okay, I'm co-waiting on this thing, I'm co-yielding here, and here I'm terminating by doing a co-return versus having big implicit state machines based on callbacks. Here the potential optimizations are, I no longer have to do all this. Can I terminate? Can I suspend my task? Do I need to cancel? How do I do that? Do I need to do manual unrolling? Does this mean I may not use no except anymore in any part of the code base because that would terminate instead of cancel? So if you see this side by side, it's obvious that this is way less code, but I can't do that on a slide without it going like this size for the font.
Okay, more questions. Here we are.
I understand why you introduced task to be able to wait on it, but why generator?
So in general, a generator is nothing but a task that can return multiple elements. But you don't want to have all elements at the same time, but can work with one element at a time. So I don't need to run the whole generator. Just like the std generator, I can just say, okay, I figured some input out. I can now work on that one. And now I can do this for loop, even though I can't write it like this right now. You can still do the same thing like a for wait, but it's not as nice to write. You need to do manual iterator use.
Do I see any hands?
Can I combine the generator with a task so that it kind of returns asynchronous elements?
Yeah, sure.
And then kind of write something like an asynchronous for loop?
Clear enough. Inside a task, you can await another task, and you can co-wait on the next element of a generator being yielded. You can wait inside a generator for another task, and you can wait for another generator inside a generator, and so on recursively, however you like.
I actually have one question, because you said it can't be no except.
Yes.
Because the new might throw.
Yes.
But if you use custom allocators, you can actually prevent that, right?
Well, yeah, that brings us back to the first coroutine transformation. That's not it. That's the slide. So here I have this comment that this is customizable. What you can do is you can provide an operator new for your promise. And if there's an operator new on your promise, the compiler will not call the global new, but will call that operator new. And in there you can do custom allocation logic. For example, having an input of allocator type, or having a template parameter that defines your allocator type you want to use. And so you can customize that allocation.
And so you could prevent the need for exceptions?
No.
Or are there other
Operator
places?
new is required by the standard to throw an exception if you run out of memory. And there's something more going on there, like you can provide another function in your promise that overrides that and allows you to have a handling for that case. Then this will need another slide.
Okay.
Obviously, you would need to do the same thing for operator delete, because you probably don't want to call the global delete after you've called a custom new. GCC actually warns about that one.
Okay, first of all, thank you for this really deep talk. And I think on slide 22 or 24, I've seen something, pattern matching,
Yeah.
const expert. Is this already
No.
final? Looks
So-
like Rust.
So this looks kind of like the pattern matching thing that we hopefully get in 29, but I'm not going to promise that. So this is heavily inspired by the paper and uses pretty much the same syntax, but this wouldn't work because you can't have a return type of void in that syntax in pattern matching, because we still don't have regular void, which we probably should have added 20 years ago.
Okay, thank you.
There was one before.
You mentioned it's hard to debug because you lose like the stack trace.
Yeah.
You said with a good debugger, is there some extension in LLDB or
Well,
GDB
for
to?
example, the Microsoft debugger allows you to provide a netwist file where you can describe how your memory layout should be interpreted by the debugger. And it can do that recursively. So you say this coroutine type should be interpreted that way. And then you'd have this parent member inside your coroutine frame. And it would be able to recursively apply that same visualization again. And now you, inside the debugger, have the reverse of your call stack of your coroutine. I have no idea how you would do the same thing, for example, in GDB.
Okay.
At one slide, you had a defer keyword.
Yeah.
Is this inspired by Zig?
No, that's, well, I think the C29 paper is inspired by this.
Okay.
I'm using this because the alternative that's valid C++ is like 3 times as long. You need to have a scope guard here, and for reasons we don't have a generic scope guard in the library, only in the library fundamental TS. And using that one would end the slide over there.
So, as far as I know, Zig introduced this defer
Well,
keyword. Could it
there are
be? Or?
multiple languages that have a defer,
Okay.
for example, Go.
Okay, go.
And I mean, this is a use case where I think it would be totally a good idea to add this to C++. But defer heavily messes with how we normally would do resource management in C++. So,
Okay.
So you could say this is pseudocode heavily inspired by C++
well,
in a way,
you can't do a slide that does this in regular C++.
and fits.
Because think about this type. Notice this question mark. We have no idea how to specify in C++ that, well, this must be a type that's in a specialization of this template without going to this level of metaprogramming. So I just stole this syntax from Java, which has this nice syntax to express, well, that's some instantiation of this thing, though it's not instantiations in Java.
Okay. Thank you very much. Please give Michael another hand. Yeah, let's wrap it up. Let's drink.